Hi, and welcome to Special Bond Types. Today we'll be looking at some compounds that have some bonds that don't exactly fit under the categories necessarily of ionic and covalent. The first one actually that we'll talk about actually is both ionic covalent and covalent bonds in it. And these are compounds that have a polyatomic ion or an ion from table E in them. So if you look at one of these molecules, within the table E ion, so if you look up sulfur and oxygen from copper sulfate, those are same side of the staircase. So there are covalent bonds between the sulfur and oxygen atoms. However, this copper is actually transferring 2 electrons over to that polyatomic ion, which is why that polyatomic ion has that -2 charge, and the copper has that +2 charge. So between those two pieces, you actually end up with an ionic bond. So just another example here, between the potassium, which is transferring 1 electron over to the nitrate group, you have an ionic bond, whereas within this molecule, you have several covalent bonds. Metallic bonds are a crystalline arrangement of cations with a mobile C of valence electrons. So what actually happens here is you have nuclei and kernel electrons that sit still. Metals are really bad at holding on to electrons, so the valence electrons move all over the place. And these form in pure metals like copper or silver. They also form in alloys, which are mixtures of metals, things like steel, brass, etc. So a lot of times students ask, okay, we talked about opposite sides of the staircase. We talked about when we have 2 things on the right in the case of a covalent bond. A metallic bond involves only things from the left side of the table. Properties of metals are important to understand, and they actually relate to this bond, which I'll give you a little bit more of a visual representation of in just a moment. Metals are able to conduct heat and electricity. You can bend them, draw them into wires. They're malleable and ductile. They're lustrous or shiny, and they have a high melting point. So to give you a little understanding of why those properties occur, so what this actually looks like, these stationary cations that you see are the nucleus of metal atoms plus the inner kernel electrons, which give them an overall net positive charge. Those valence electrons are not held very tightly by the individual metal atoms because metals suck at holding on to their electrons. So these electrons that you see out here, you don't actually know who they belong to. They're in this mobile sea of valence electrons that allow them to move around. So those mobile valence electrons are actually what basically make metals have the properties that they do. So for example, if you put an electron in over here, it's going to bump into other electrons, bump into other electrons, bump into other electrons, until eventually over here, another electron will pop out the other side. So because these electrons are very mobile, so we have that mobility of these valence electrons, that creates conductivity. So electricity is a flow of electrons. Whenever an electron is put in on one side, it repels electrons, pushing them through the sample of the metal. So that's actually what's occurring in wires. This gives us, this is very important, mobile charged particles. So because we have mobile charged particles, that's why we're going to have electrical conductivity. So if a question asks you why a metal conducts, it really ties back into that idea of low electronegativity. Metals don't hold on to electrons well. Because of that, electrons are easily moved throughout the sample of a metal, causing conductivity. Malleability. So we talked before about, if you strike an ionic compound and you disturb that crystal, you have a lot of repulsion there, which are why ionic crystals are brittle. If you were to actually take a hammer and just pound on that guy right there, if you move this guy a little bit, it really won't cause that much repulsion because you still have this like cushion of negative charges that remain between those individual cations. You can imagine even if you tried to push some of these cations together, those mobile electrons are able to stay in between them and create a sort of almost padding, if you will, that prevents repulsion. So repulsion is prevented by those mobile valence electrons. And actually, one more thing related to this, some people ask about luster. The reason that metals reflect light so much and are so shiny is really because those electrons can move around as easily as well. This has to do kind of with thinking about electrons jumping from higher and lower energy levels. These electrons have a lot of freedom to move around, and therefore, they're jumping up and down, they're giving off light, they're therefore reflecting. Network solids are compounds that have a whole bunch of atoms covalently bonded together. So these do fall under, molecular covalently bonded compounds. They're just a little bit different from a regular molecular compound in that they have a large number of these bonds in them, which affects their properties. So a couple of examples for you. A quartz crystal is an interwoven helical chain of silicones and oxygens bonded together. So when you look at this picture, you see lots and lots, not a great color choice, lots and lots and lots of bonds. Another example that we've talked about in the past are diamonds. Diamonds have a tetrahedral arrangement of carbon atoms. Each of these carbon atoms forms four bonds with other carbon atoms. So you have a lot of individual bonds occurring here. Individual covalent bonds are, moderately strong. They're not anything crazy, but because there are so many of them all working together, this is going to relate to their overall structure. So the properties of these compounds, they have very high melting points, high hardness. You know that about diamonds, hardest material, they always tell you. And they don't have any mobile electrons. Everything's locked into place, so nothing conducts. So when we talk about these properties, the very high melting point, so property number one, the high melting point, it's very difficult to break so many bonds. So you would actually need to break these forces, these bonds. We have very strong intermolecular forces here in order to allow those atoms to flow. You're not able to do that because there's just so many of them all working together. This is actually also the reason that these are so hard. In order to break something, you're breaking bonds in it. It's not easy to do that. And number three, they do not conduct because electrons are firmly held in those covalent bonds. They can't move. If you don't have mobile charged particles, you do not have conductivity.